for the remainder of this class. And for that, the environment is very, very similar in terms of you first, if you want to create a box or a tube, you have to first create a rectangle. With a rectangle, then you have to create another rectangle inside of it. You have to select the surface area in between it. And first you have to identify which plane you want to actually start from. So we start from that plane. We again go through a particular rectangle. We go and select that rectangle. And then from that, we go from the origin, and the dimensions were 790 by 790 millimeters, right? Again, you can change those units in the tools section here in Inventor if you really want to, but it starts with the millimeters, so let's keep it like that as well. Then you go again, the crude way that I like to define that is you go 20 millimeters to the right, 20 millimeters down if you have done the envelope part of it, and then from one corner and then to another corner, because that's how you define a rectangle with 2 points and 2 corners. Or in this case, it's going to be a square, not a rectangle. And then you do a 20 by 20. And then again, you go to your rectangle, you get from one point to another. And now you have your 2 rectangles there. You go and you basically delete the extra parts there that existed. And then from that, you essentially go and take it from there. And then once you have that, you go and select the one that you have on the other side, and then you extrude it as much as you can. You essentially extrude it up. And in this situation, it's a 4-meter extrusion that we're requiring because the height of our column is 4 meters. So you do the 4,000 millimeters there. Once you have that, then the next step is to have that base, basically the footing of the column or this tube that we've created here, or this hollow structural section. Again, what we do is we have to find the exact same plane that we've modeled this for. So we do the orthogonal plane at the very, very bottom. We again go and introduce our larger rectangle. And again, this is going to be a 2 centimeter by 2 centimeter extra. This is just, again, for the requirements for your constraints and the supports there, nothing more. You go again 20 by 20. Get another one here, 20. And then once you have this, then you get from one side of it, again with the rectangle command, to another side, and you have this nice rectangle there. So then you go and finish sketch. Once you go and finish that sketch, you go ahead and do the extrusion. And then this time, the good thing about Fusion is that if you do negatives, it understands it. So if your extrusion is positive, let's say 4,000, it goes up. If it's negative, it goes down. So this is something that I did not find in Inventor, which was quite challenging, because then you have to go and make sure that it is actually extruding in the proper direction. Then once you have this, this is essentially your element and that tube. As you can see, it was quite simple to perform it here in Fusion. However, it was quite similar in that sense in Inventor as well. But I found the tools up here in Fusion a bit more interesting. Once you finish that, then you have the opportunity to, of course, perform some generative design, but we're going to do a simulation. And that simulation is the shape optimization simulation that we talked about here. We go there, and then here you basically have to go to that pre-check. So this is some other feature that I actually didn't mind here, was that the pre-check tells you what you need to provide in order for it to perform that shape optimization. So the first part is the material. Let's say we go to a particular type of material. Again, in the shape optimization, most likely the material is not going to be a factor in the optimization of the mass and the minimization of the mass. so this is not, again, it's not a shape optimization. You know, it's a mass minimization problem. I like to call it that way, but they call it shape optimization. Once you have the material is going to be good for afterwards when we recheck it. So once we have that shredded off nice bits and pieces by means of our load distribution, then you can now go and take it from there and reevaluate it. So the first thing is that we provide the constraints, then we provide the loads. So this again is a structural load. I will identify it as a pressure, and then I would assign a particular face to it, and then our 1.7 megapascals that you have there. Once we have all of these aspects, then we can also go to the shape optimization there tab, and then you can define your preserved region. And this is again similar to the shape generator in Inventor, where you can define where around the whole basically element and component do we want to make sure that is preserved and it does not change, or it's not really shredded off anything. And typically, again, as I mentioned, around the load, where the load is actually directly applied. And the second part is where you have your nice constraints for your support. So again, you do that, make sure that the whole support, that is not a part of our optimization at all. So we basically increase that. Okay. And once we have that and we're satisfied with the preserved region, we go and we say okay. And then once we have this, then the next part is that we can also play around with our let's say optimization criteria. There are some, you know, with respect to maximization of stiffness and the target mass, which by means of, you know, how much maximum mass do we want to basically reduce. In this case, a maximum of 30%, but we can change it. We can do, say, 90%, or let's say only 30% is going to be left. This could be, let's say, 50% left, depends upon how much we want to shred. So 30% means that 70% of it would be taken. And then once we have that, we go to the pre-check. We make sure that the pre-check is good, and then we go to the solver. The solver is performed on the cloud, and you have enough credits basically, but with your student account, you would be able to perform it properly. And then you save your project. Let's say this is lecture 3 project. Then once you have that, then it basically goes on the cloud, and once it finishes, it gives you an update that this is finished, and then you can basically take a look at it. And it goes by pretty fast, I found. Anyways, by the magic of pre-recording this, I have this shape here that and this optimized region here. As you can see, you can play around and reduce it a bit, and then you can see where the critical points are that are taking the majority of the weight. And as you can see, even though this is a completely symmetrical shape, the optimized shape is not symmetric, at least about the axes that we are looking for, which are the basic axes that it is symmetrical about the basically diagonal axes, but it's not with respect to our actual axes that we have there. So here, what is interesting is that this has happened by means of us utilizing a larger mesh. If we want to promote it, we can go and promote it there and see how it is. And this now takes it back to our modeling environment, where we have to now shred it and model it. Now, something like this would be a bit more challenging to be able to model, because now you have to do it basically in a particular orientation, and those essential you know, those places don't exist. It's harder to be able to take it. Now it's not impossible, but it's a bit more challenging. Whereas if it's completely symmetrical on one basically face, and then you want to go around it, it would be a bit easier in that regard. So then what has ended up happening here is that this is an optimization, an optimized basically part where I've actually increased the mesh size. So as you can see, when I increased the mesh size and kept everything else the same as the same part, now a more symmetrical, and this is more similar to what we had in Inventor compared to the original one that was a bit, you know, slanting and a bit essentially not symmetrical about the planes that we're able to easily model. And now we have this shape and this geometry that is an optimized geometry. What we now have to do is we now have to go and promote this. So we go and say promote, and it promotes it where we basically have saved our simulation. Once we have performed this, then these are the two essentially meshes that we had. This is with a larger mesh size. And the other one is with a smaller mesh size. So completely two separate structures, one much more symmetrical and much more pleasing for us, and easier, much more easier to model as well. And I'm going to be focusing on this for the modeling today. So what we do is we basically go to the essential simplify solid. We can remove, let's say, the original box and all of these aspects if we're satisfied with this model. Even we could remove this mesh body here too. And then what we can perform here is, again, we go to that create, and then we find one of these surfaces. Really, this is the beauty of it when it's symmetrical. So we find one of these surfaces and we go and model only one side of it. And once we model one side of it, we mirror it and then take it from there. But for this, it was a bit simpler for me, I found, compared to Inventor, because it was just so much easier. And actually, the final model is much more in tune with an actual symmetry, even though we have some approximation with our mesh. It's quite symmetrical between this surface and the surface behind it, as you can see visibly. It's obvious. So you go and find that middle basically line that we're going to be doing our nice mirroring from, so that we only model one side of it, and then we utilize that side and then mirror it back again. Okay, so we do more or less the same that we performed with the other basic Inventor. We start from a particular point. We can also utilize our spline function, but we'll be focusing on purely our line. And then we go on top of it, and then we find where it is, and then we basically say, okay. Then we go on the bottom and we perform the exact same thing. We can, of course, do it in multiple different portions. And then if we're okay with it, then we go to the next part. And the next part is to perform essentially the side, the left-hand side, and then the top parts as well. Basically do it in a few sections so that it kind of approximates that nice shape there and the curves there as well. Take it from there. Again, the closer you get, the better it's going to be, but you can also use a spline to be able to to make a bit more of a let's say smoother section there. Then you go down from there, and you want to attach it there to where it was attached in the beginning. So here it looks like it found it in a different place, but you can always move it around from this area and then kind of intuitively put it on top of the line that already existed. And then sometimes it might happen like this, there, where you have to play around with it and take it from there. Maybe like that line there needs to also be changed in the location. And the good thing about the software is it's quite intuitive in that sense. You just click on it, then move it around. And then you go with the fillet. You essentially do it between every two. Again, I emphasize that this is to minimize the propagation of cracks. So in every element, it's good for us to be able to have, instead of having very sharp edges, you have to have kind of a curvature there as well, and minimize the stress concentration. Here, the other thing is that once you do those and you have those fillets, you can actually go on top of it and play around with it and actually change the dimensions of those fillets as well. That is more or less what would provide it with a very good, nice structure that you might be able to use. And this is how you do it. So that arrow sign, you can actually pull it and push it. And with that, you can change the radius of that fillet. Once you have that, then the top part as well is the last part that you need to take into consideration. As you can see, it already has understood that this is the part that needs to be mirrored there. You again perform the exact same thing on the top part as well. You can go from, let's say, there, and then just have that. And then between those, I wanted to do a nice fillet. So what I did was I did this. And there you have it. You don't need to do any other fillets between, let's say, the middle line, because we take it to the other side there. What we do is we basically go and select essentially what we want to be reflected on the other side. So we go and select all of these. Once we've selected all of them, we go to the mirror function there. Okay. Make sure that everything is selected, and then it says what is selected, and then it basically gives you the option to provide the mirror line. You check and recheck, make sure everything is good, and then you say okay, and then it's been basically mirrored on both sides there. You can play it from there, reduce it. You make sure that everything is fine. Once you ensure everything is fine, basically what you do is you go and finish your sketch. Once you finish your sketch, that is essentially where you can now go and plug it in and extrude it. And then once you extrude it, you would be able to basically capitalize on the actual finished structure. So you go there, you click on it, you go to extrude, and then it gives you how much you want to extrude. So if you go to the top, it basically gives you the direction. Direction is typically orthogonal to whatever surface it is that you want to extrude. So how much do you want to extrude? You want to extrude exactly the 790. That is the dimension of one of the sides of your square, right? So now it's extruded that, and it goes there. Now what you have is a situation where you want to now have a completely symmetrical, let's say, surface on the other side as well that needs to be extruded. So what I do is I go and I this time go to the create again, and I go to the modify, and I try to see how I can actually go and rotate this. Essentially, my objective is not necessarily to directly rotate it, is to create what we call a polar array of this. So I want to create a duplicate of this, but just in 90 degrees. So we go and we find where we have to do this. We go and it asks us with what axes we want to do it with the orthogonal axes. We want to only do 2 in quantity, and I want to do an angle of only 90 degrees. So this is what we call a polar array. It's very, very famous. And then what ends up happening is that basically whatever we have here, it rotates in 90 degrees and about that particular axis that we've defined. So then now we have this exact object, but on the other side. The next part is for us to exactly move it. So we go and we move it in what direction? We want to move it in this direction, but how much? Negative 790, right? That is exactly what we have. Now we have 2 intertwined structures. What do we have to do? We have to now find the intersection. We go into the simplify surface in the modify section, and then we go into the combine there command. On top there, I just missed it. Yeah, this combine, and then we go to the combine command. We click it, and then you have to select intersect, and then you say okay. So it gives you this nice, interesting part. You can see there's something inside of it, right? We need to be able to remove that. Why? Because that is not a part of what we are interested in, right? So for that, what I typically do is that I create a box inside of it with that, basically that bottom part, and then extrude it downward. And once you extrude it downward, it actually creates a hollow section. So this is what I have to do. You do create, you select the surface, which is anything on the top would be the surface that you want to start your sketch. Then you again go into the rectangle command. And then from the inside. And then once you have the inside there, then you go and extrude it, this one downwards. Downward how much? Minus 4,000. Okay, when you do that, ta-da, we have a beautiful section that basically represents what we have provided, is completely symmetrical, about every 90 degrees. And that's what we can utilize, and that would be basically our optimized part. Now, you know, this is not a perfect modeling, of course. It's just for demonstration for you, but for your project, I'm expecting you to go a bit more creative, try to do it as perfectly as possible, and take it from there. Once we have this is now our final result. We now need to go and see how we would be able to go, and of course we have to promote it and simplify it and all these types of things. Then once we have this, we have to go and essentially do the analysis again. So we go finish results. We have our finished results there. Now we have to do another simulation. We do a new simulation study, this time with our static stress. Once we do that, we create the study. We now go and try to do it again and see what the results are going to be. So this is our first static simulation. This is where, of course, you do the exact same thing. So with the static simulation, you need to again provide the constraints. You have to create another nice area there, because that was not a part of the optimized shape. We basically constrain that there on the bottom. We add the load on the top, again, a pressure load, which is a static force. Again, we perform that 1.7 megapascals. Now, this is where the material becomes quite a bit in handy, where you have to perform and select the material properties there. So you can change it. This one, for instance, the material that it has there had a Young's modulus of 31 gigapascals. And as you know, if a structure is subjected to an axial load, the amount of displacement is going to be PL divided by AE. P is your at any section, right? Because if it's P, your force, L is the length of your element. A is the cross section at a particular cross section that you're considering for your stress. And then E is your Young's modulus. That means that if the Young's modulus is larger, the amount of displacement is going to be smaller, right? If it's smaller, then it's going to be larger. That means for steel, the Young's modulus is quite high. So it's going to be, the displacement is going to be much smaller. So here, for instance, for steel, you have 0.8 millimeters. That means it's very, very little. Of course, this is very exaggerated, right? It's not actually displacing this much. This is 0.8 millimeters at the maximum. So that is for steel. Now, I want to, let's say, change this and revise this in terms of, instead of steel, we go and do, let's say, a plastic or something like that, or aluminum, however it is. We go and let's say we do our polycarbonates, which is something that is utilized, let's say, for higher strength for these 3D printing platforms as a filament. We go again, we solve it. This time we can also do it locally. I have almost a supercomputer with 64 cores in my office, so I like to do it locally, but you can of course do it on the cloud. I believe my computer and the cloud are almost on par. Essentially, the portion of the cloud that they, of course, provided to us to do the analysis. So then this time it ended up being about 7 millimeters, so it's quite larger. What this means is for that particular material, you cannot shred as much as we have shredded here. We have to shred a bit less there, right? So that's what that means. What you can also take a look at, you have to, and this is a part of your term project, is instead of doing it from the materials library, I would like you to go and research on how you would be able to add a new material and then go to the ASTM standard, go to other types of standards online, and then see what type of material properties it actually has, plug it in so that you can finalize the results. Now for this, let's say I go and this time, instead of plastic and polycarbonates, I go and I select, let's say, aluminum. And you have various different ones, but if you want a particular filament, particular type, this is, of course, a part of your project. I would like you to go and research that and make sure that the transition is correct. So let's say moderate aluminum, they have some standardization there. And essentially, you can take a look at the properties there as well. Now, if we have the aluminum there, and then, of course, this is another way that you can browse through the material, and you can add the material there as well if you want. Some of those tabs, like the ones on the bottom here, you would be able to add that. So you go and this time, again, solve it. Again, I'm going to do it locally. I'll solve this. And once this time it's solved again, now we go and take a look this time what type of displacement we're expecting from this. So this time we have 0.2 millimeters in our displacement, right? So if we have the 0.2 millimeters on our displacement, it's pretty good, very good in that sense. So your objective based on the term project is that this basically platform and this column should not displace more than 3 millimeters. If it does displace more than 3 millimeters, you have to either go back change some of those aspects of it, maybe shred a bit less, or maybe change your material properties. See how it is. You have to use the proper, correct material property that you use. If it does not exist, which it does not exist in the regular library, you have to go and search it. Let's say a particular filament that you go and see online, and then you go and see the ASTM specific characteristics in terms of yield stress, in terms of ultimate strength, in terms of the strain, in terms of the elongation. All of these are Young's modulus, which is very, very important, particularly for the axial. So that's